All right. So, hi everyone. I'm Chirag, and this is the talk about the work in my dissertation. So, as I go through this talk, feel free to interrupt me at any point for questions. And if you're on the Zoom call, then you can either put it in the chat or just go ahead and say it over voice. So, over the past decade, we've seen a huge variety of artificial intelligence or AI applications emerge. We've got AI assistants, generative AI, new computer vision applications, and many other applications. And one of the core techniques that's enabled all of this is called deep learning, or DL. Deep learning applications are quickly growing in scale and diversity, so the resources they consume have also been quickly growing. For example, over the lifetime of a single modern deep learning application, it's estimated that a computing system consumes 50 times the energy of a car's lifetime. And this consumption can be broken down into two stages. The first stage is when the application is being developed, and that's called training. And training is estimated to consume 5 times the energy of a car's lifetime. And the second stage is when the application is deployed for use, and that's called inference. And although a single pass of inference consumes relatively lower energy than training, over the lifetime of the application, it's estimated to consume the remaining 45% the energy of a car's lifetime. And because inference dominates the energy consumption, I focus on inference in this work. So these numbers, it's just a specific deep learning model. In this case, this was GPT-2 for these numbers. So the numbers are already huge and they appear to be growing larger. And so to demonstrate this growth, I plot the average computational resources in log scale measured in gigaflops for one pass of inference. And I plot it for models across the past 12 years. And so we can see that there's been an exponential increase in the computational resources consumed. And if this trend continues, then deep learning is estimated to consume 0.5% of the world's energy by 2027. And so it's clearly important for us to mitigate the cost of this growth. And fortunately, we've developed several methods to do so. And one of them that's especially promising is to employ deep learning accelerators. So deep learning accelerators, or DLAs, are processors that are built specifically for deep learning workloads. And they comprise two main components. The first is a compute cluster that's made up of a grid of simple computational units. And the second is a bespoke memory hierarchy that's designed to efficiently move data around for the deep learning workload. Because DLAs have a simple high-level architecture and only need to support deep learning workloads, they don't need many of the components present in traditional processors, namely CPUs and GPUs. And so consequently, DLAs are more area efficient and energy efficient than CPUs and GPUs when executing deep learning workloads. So deep learning accelerators are an important tool for us to mitigate the growing cost of deep learning. Because of their relative simplicity and the significant benefit that they provide, DLA development is more widespread than CPU or GPU development. For example, for large deep learning applications that run in a data center, a specialized DLA may be developed with a large compute cluster and a deep memory hierarchy. Or for a low power application, like processing sensor data in a battery-operated device, a specialized DLA may be developed with a small compute cluster and a shallow memory hierarchy. And finally, for some niche application, it may actually be cost-effective to develop a niche DLA with a shallow memory hierarchy and long but narrow compute cluster. Unfortunately, despite their relative simplicity, DLA development is still costly and time-consuming. And because so many parties are involved in DLA development, this effort is multiplied across the industry, more so than even CPU or GPU development. Thus, it's advantageous for us to try to reduce the cost of this development, and that's the focus of today's talk. So we observed earlier that many DLAs have similar high-level architectures and differ primarily in specific design parameters, such as the size of the compute cluster. This means that DLA development is a prime candidate to apply automation. And more specifically, what I mean is we can design tools that automatically explore the values of these design parameters, to find DLA designs that satisfy the various design constraints. And this process is rather intuitively called design space exploration, or DSE. So unfortunately, DSE is also challenging. Looking at deep learning from an end-to-end perspective, there are many tunable parameters. And I visualize the design space of these tunable parameters as a 2D box here, but in practice, there would be many more dimensions. Furthermore, the parameters in this design space have complex interactions among one another. For example, many of the designs are infeasible or invalid. And so here, I mark the feasible designs in orange, and you can see they form a complicated subset of the full design space. Furthermore, there can be performance cliffs inside this design space as well. So I marked the performance of each of these designs as a heat map, just from good to bad. And if we take a look at this region, we can see that there's a dramatic change in performance from green to red, even when the designs are only changed slightly. So of course, this is just a caricature of the design space, but prior work has consistently shown that these are real issues that need to be solved. And that brings us to the central goal of this work. I show how to overcome these challenges by incorporating prior knowledge to efficiently design deep learning accelerators. The key contributions of this work are, first of all, a technique that provides handcrafted prior knowledge to improve the efficiency of design space exploration. Second is a technique that leverages prior knowledge to learn to predict the performance of a DLA. And third are open source tools that implement these techniques to reduce the development effort of DLAs. So for the remainder of this talk, first I provide some brief background that's necessary to understand the talk, and I also make the design space more concrete and discuss the scope of this work. Then I present the first open source tool, which is called Spotlight. And that's a tool that's designed to reduce development effort in the earlier stages of DLA development. What I mean here specifically is when design decisions are evaluated using an analytical model. And to reduce development effort later in the DLA development cycle, I present another open source tool called Polaris, which is intended to be used when design decisions are evaluated using RTL simulation. Before presenting Polaris, though, I present an open source tool called Starlight, which is pretty much the bulk of how Polaris actually works. And so the order in which I present is Spotlight, then Starlight, then Polaris. And finally, I finish with some concluding thoughts. So I start off with some background. The deep learning stack encompasses many areas, and design space exploration can be applied to any or all of these areas. At the top of the stack is a deep learning model. And a deep learning model comprises a series of connected layers. In this figure, there's 3 layers from left to right. And they're trained to perform some prediction task. Next, the deep learning model is translated into a program that can actually run on the hardware. And the term we use to describe this kind of program is a software mapping. And the software mapping is then run on the DLA, as we discussed before. When designing a DLA, the design parameters of the software mapping can have significant impact on performance. And so in this work, we explore the joint design spaces of the software mapping and the DLA architecture. And so designing DLAs with this approach is called hardware-software co-design. And I now define each of those design spaces more concretely. As I mentioned previously, a DLA comprises 2 primary components. First is the compute core. And inside the compute core is a grid of simple computational units called processing elements that typically compute 1 or more multiply accumulate operations. Second is the memory hierarchy. And the memory hierarchy consists of on-chip memories that provide faster access to DRAM than the main memory structure, which is data, than the main memory structure that's called DRAM. And so here we have 2 on-chip memories, the global buffer and the L2. So in the DLA architecture,
So do you not consider new memory kinds of architectures?
No, for this work, we focus on accelerators that are usually like on an SoC. So there would be actually a shared L2 and shared DRAM. So yeah, in the DLA architecture design space, we have the compute core shapes and the memory sizes. Now I present the design space of the software mapping, where the software mapping is the software implementation of a single layer of a deep learning model. And a common target for acceleration and for building software mappings is the convolution operation, because it can represent a wide range of common operations in deep learning models. And so in this work, the software mappings are all implemented as a convolution operation. So the convolution is computed as follows. It's not important to understand all the details, so I'll draw your attention to two things. There are 7 loops total used to compute a convolution, and they're parameterized by these 7 dimensions. And the software mapping design space is the set of loop transformations that can be applied to this loop structure. The first type of transformation is the loop order. So there are 7 factorial possible loop orders, and the specific order affects the lifetime of data in the on-chip memories, and it affects performance. So it's an important design parameter to explore, and we add it to our list of explorable design parameters. Another transformation is loop tiling. So what I've done here is I've broken the S loop into 2 pieces, S0 and S1, and each of these pieces is called a tile. Loop tiling is a common optimization to ensure that data is reused in the on-chip memories to reduce slow trips to and from DRAM. So it also affects performance, and we also add it to our design space. And the final transformation that we look at is spatial unrolling. One of these loops can be spatially unrolled across the horizontal dimension of the compute cluster, and another loop can be spatially unrolled across the vertical dimension. So here what I've done is I've spatially unrolled the C dimension. And the spatial unrolling affects the amount of parallelism available in the software mapping. And so again, it affects performance, and we include it in our design space. And so that's what our final design space looks like. So with the background out of the way, we look at our first tool, which is Spotlight. At a high level, Spotlight is a hardware-software co-design tool. And what that means more concretely is that the inputs to Spotlight are a hardware budget and 1 or more deep learning models. And the outputs are an optimized DLA architecture and optimized software mappings for running the deep learning model on the DLA. The main component of a hardware-software co-design tool is an optimizer, which tries to find these optimized design parameters. For Spotlight, the optimizer selects a candidate, evaluates it on an analytical model, and then it uses that evaluation to guide the selection to the next candidate. The selection of the next candidate. This process continues until an optimized design is found, or for some number of fixed trials. And a hardware-software co-design tool is really just a wrapper around the optimizer, so I dig into that a little bit more.
How do you know when you said it continues into an optimized designs file?
Yeah.
How do you know when it's found?
So it either does a fixed number of trials, or if the change in the design is too small between iterations, then it considers it to be some kind of optima. It may not be the global optima, but it stops at that point. And it's like a pretty small epsilon. So for the optimizer requirements, first of all, the optimizer doesn't know anything about the analytical model. All it can do is evaluate specific design candidates. And this type of optimization is known as black box optimization. And second, to reduce the number of candidates that are evaluated, which can be very important for hardware design because it may be expensive to evaluate candidates, the optimizer must be sample efficient, meaning it quickly converges to optimized designs. And third, the optimizer must be able to handle the challenging design space that I described earlier. More specifically, it must be able to handle complex interactions among high-dimensional parameters. As a starting point, we use a kind of optimization framework called Bayesian optimization, or BO, because BO has been used for problems with similar requirements. A Bayesian optimizer has 2 components. The first is something called a surrogate model, which is the probabilistic proxy model that predicts performance. Try saying that quickly 3 times. And we show it as a scripted M. To predict the performance of a design, it's plugged into the surrogate model. And because of how BO works, the surrogate model doesn't produce a scalar prediction, but rather it samples from a normal distribution. where the mean of the distribution can be interpreted as the model's prediction, and the standard deviation can be interpreted as the model's uncertainty in that prediction. I won't go into too many details here, but this is integral to how BO typically works. The other component of a BO framework is the acquisition function, which is a function over the surrogate model that selects the next candidate to evaluate. And we show it with a scripted A, and it's used like so. So the operation of a Bayesian optimizer is as follows. First, it evaluates a batch of random candidates on the acquisition function. Second, it selects the most promising candidate as measured by the acquisition function. Third, it evaluates that candidate on the analytical model. And fourth, it retrains the surrogate model with the new evaluation and repeats this process.
I think it's the most promising.
So the acquisition function can be, there's different options for it. One of them is you just add the mean and one standard deviation, and you just take whichever point maximizes the function. So it's essentially saying that either the point is really good if the mean is high and the standard deviation is low, or if the mean is middling but it has a high standard deviation, then it would also possibly select that point. And the purpose is that it kind of balances exploration and exploitation. And there's a few different options. That's one of the more simple ones, but it's actually what we use in Spotlight. It's called upper confidence bound. Okay, so these are the steps for a Bayesian optimizer. And if we look back at our optimizer requirements, BO is indeed a black box optimizer. So the first requirement is satisfied. And because BO uses the surrogate model and acquisition function, it's sample efficient with the candidates that it evaluates on an analytical model. Unfortunately, standard options for the surrogate model, in particular, something called a Gaussian process, which is typically used, struggle with the complex constraints and high dimensions of the input space. And that brings us to our first key contribution. We transform the hardware-software design space with a function f that's easier for the surrogate model to learn. So rather than predicting the performance of a design directly, the surrogate model predicts the performance of the transformed design space. So the purpose of f is to create a function that's easier for the surrogate model to learn. And if we bring back that performance from earlier, we could apply some hypothetical f that would transform the space into something maybe with lower dimensions and also something that's easier to learn from. And of course, if we could define a perfect f, then we wouldn't need an optimizer to begin with anyway. And so instead, we have some guidelines for what to include in f. First is that f should reduce the dimensionality of the input space so that it's easier for the Gaussian process surrogate model to be able to learn from. Second, f should transform categorical parameters into cardinals. And so, for example, the spatial dimension I mentioned earlier is just one of 7 possibilities, 7 arbitrary possibilities, but it could be transformed into something more meaningful, as I'll show shortly. And then the third guideline is f can be used to inject domain information into the search. So here's an example of some type of f. Given the compute core shape, the loop tiles, and the categorical parameter of spatial dimension, f can compute utilization, and it's much easier to learn the properties of the utilization function than it is to learn the properties of the constituent parameters that make up f.
So why is that?
So going back to this, utilization would tend to be like more linear, for example, or maybe has some like exponential drop off or something.
So it just happens to be true for utilization. It's not necessarily. Right, I mean.
Oh yeah. So this is just a guideline for f, and the goal is we did a fair bit of analysis to try to figure out what kind of correlations would be beneficial to put into f. So this is one example that we actually do end up using, and there's a handful of others like the DRAM utilization or the approximate number of iterations for computing the workload, and we just kind of find these empirically and using some statistical methods. But yeah, we have a full list of, actually I forgot to put that, but there's a full list I can show of what goes into f. Okay, so with our definition of F, then we've now satisfied the third requirement for our optimizer. And so now I show the results of
Hey,
Spotlight.
Chirag, question, sorry. So did you mean that F, the computation of utilization is easier to learn? Or did you mean that once you have utilization, your performance and energy projections are easy to learn?
Can you repeat the question?
Yeah, the question was, when you have F, is it easier to predict F, or is it easier to predict the energy and delay metrics given F? And it is the latter. So the purpose of the surrogate model is to predict the performance. But if the input is the transformed space, it's easier to correlate that input space with the performance metrics.
Okay.
So the transformed space is basically constructing features.
Yes. Yeah, they're handcrafted features, more or less, rather than learning it using like a data-driven approach. Although we do also show that in when I get to this, the Starlight section. Okay, so now I show some of the results for Spotlight, which implement this technique of doing a feature transformation. We compare the designs produced by Spotlight against the designs produced by two other state-of-the-art hardware software co-design tools that perform evaluations in the same infrastructure as Spotlight, so they can be directly compared. And those are called Confucius and Haskell. And then we also compare the designs produced by Spotlight to 3 hand-designed accelerators that have also been modeled in the same infrastructure as Spotlight. And those are Iris, NVDLA, and Mary. And we evaluate them using 4 important vision models, specifically VGG16, ResNet50, MobileNet V2, and MNASNet. And we also use one natural language processing model, the transformer.
You're comparing against fairly old designs, especially the speed that would be.
Yeah.
Is there a reason for that?
So part of it was just that this work was done a little while ago, but also it's the infrastructure we used. I guess there's limited other tools that use it. So it's actually hard to find things to directly compare against. And so we had to implement like Iris and VDLA and Mary, and we could try implementing others as well. I do implement, in addition to this, like cloud scale versions of these accelerators and compare against that. And I don't show those in the main slides, but I can show that afterward. So on the y-axis here, I plot the delay of the resulting designs in log scale. So lower is better. And this is the performance of the designs produced by the hardware software co-design tools Confucius and Haskell. And this is the performance of the designs produced these are the hand-designed accelerators. And then this is the performance of the designs produced by Spotlight. And we see that Spotlight's design achieves much lower delay than the baselines. And I do want to point out here that it's not just optimizing delay. It's also, it has the constraint of not building accelerators with higher area or power consumption than the Iris accelerator. So we kind of normalize all of these to Iris.
Is this for like batch 1?
What do you mean?
Is there a batch?
No. Or what do you mean by batch, I guess?
Just one sample at a time, or?
Oh, yeah. So it does evaluate a batch on the surrogate model, but it evaluates candidates one at a time on the analytical model. So it's sequential.
So this result is.
Oh, this is at the end of, we do 100 iterations of hardware co-design, hardware design, 100 of software, and this is the final result.
But the latency is for what?
Oh, sorry. It's for executing a single passive inference. Yeah.
Coming in as a single request.
Yes.
Not as,
Yes.
you cannot batch 1,000 and then you count how long it takes to do 1,000. And like, there's no throughput involved here at all. Throughput is one over cycle.
Yeah. No, we didn't measure that. For this, we did a single end-to-end, we didn't do a batch. We did a single request end-to-end for the whole model. Okay.
Hey, Chirag, so you said the design space for this search was about 100 hardware designs. Is that right?
Yeah. So what this does is it does optimization layer by layer. And
Okay.
so it kind of does this approach, which a lot of DSE tools do, which is it has a hardware optimizer and a software optimizer. And so
Uh-huh.
we run 100 iterations of the hardware optimizer and 100 iterations of the software optimizer for each layer.
But for each hardware design, do you run the software optimizer as an inner loop?
Yes,
Or
as
do
an
you-
inner loop for the whole model. And we aggregate just the results of like each of the software optimizers for each layer.
Okay, that makes sense. And so let's say you say you went through 100 hardware designs. What do you have a sense for what the complete design space is? How big the complete design space is?
Well,
Can you repeat the question?
oh yeah, sorry. So the question was, do we have a sense for how big the design space is? And I have a sense for how big the sort of naive calculation of the design space is,
Yeah,
where you
sure.
multiply the parameters, and that's about 10 to the 18th for
Okay.
a single layer.
Okay. So
And
what gives you the confidence that you converged to a reasonably optimal point within that massive design space?
yeah, that's a good question.
Or repeat?
Sorry, yes. He asked, what gives us confidence that we've converged to an optimized design in the design space? There's a couple of things we don't know for certain because we can't exhaustively enumerate the space. One sort of just empirical thing is like, okay, we're doing better than prior work, so the designs are more optimized. But also when we look at the behavior of the optimization, like as it progresses, each iteration, then we do see it kind of plateauing. So it is finding some kind of optima. It may not be the global optima, and I'm not exactly sure how we would validate that.
Yeah, that's fair. And I feel your pain.
Yeah.
Get a question.
Yeah, what level of granularity do you look at the software? Do you look at C++ and say, this does like a DMA, and then how does like that translate to the hardware?
Yeah, so this is all done within, I guess for the people on Zoom, the question was, what granularity do we look at for the software space? And for this, it was all done with an analytical model. So it's actually pretty abstracted. All you give it is the shape of the operation, like those 7 parameters that I described earlier. And it actually doesn't even include things like the activation function between layers. So it's pretty abstracted, and it's meant to be a rough approximation. Okay, any other questions on this? Okay, so we performed this same experiment for all the other models that we wanted to evaluate. And across the board, we see that Spotlight's designs achieve the lowest delay. And note that some of the bars are missing because those tools just don't support all the models that we evaluated. But one aspect, so Spotlight is empirically performing well, but one aspect I wanted to draw attention to is the accuracy of the surrogate model. One out of the best 20 designs that Spotlight explores, only 50% of them are actually predicted to be in the top 20 by the surrogate model before they're evaluated. So the accuracy is not great. And in fact, out of all the designs explored, only 11% of them are predicted accurately.
What's your definition of predicted accuracy?
I'm using Spearman rank correlation, which is a way of measuring the relative ordering. So I measure the relative ordering of what was predicted versus the ground truth. And then I don't actually know how Spearman rank correlation is computed, but there's some metric that turns it into a number from -1 to 1. And so 11% is it's basically like almost uncorrelated. It's quite poor. But we do see that Spotlight performs well empirically, but also we recognize that there is room for improvement. And so that leads us to our next bit of work. And that's called Starlight. And Starlight is something that we build for use in the later stages of the DLA development cycle. And specifically what I mean is that Starlight is a surrogate model that accurately predicts the performance of a DLA as measured by RTL simulation. And because RTL simulation is harder to predict than an analytical model, we kind of just discard the surrogate model, the inaccurate surrogate model from Spotlight, and we build Starlight from the ground up for this new use case. And so we built Starlight to satisfy the following requirements. First of all, as I mentioned before, Starlight should have high accuracy when predicting the performance measured by RTL simulation. Second, because Starlight is intended for use within a hardware-software co-design tool, Starlight should be usable as a surrogate model for Bayesian optimization. And what that means is that it must produce that probabilistic normal distribution rather than just a sole performance prediction. And third, because RTL simulation results are slow, they're hard to collect, and so we want to be sample efficient with the training set size. So Starlight should be trained on a small number of samples. To satisfy these requirements, we make a few key observations. The first observation is from prior work, which develops a neural network to accurately predict the performance measured by RTL simulation. And so that sort of satisfies our first requirement. For the second requirement, we make another observation from prior work, which is that Wilson et al. Show how to adapt a neural network for use as a surrogate model within a BO framework. And this technique is known as deep kernel learning, and it's a fairly niche technique. Actually, we weren't even able to find popular libraries that implement it, but it does satisfy our second requirement. And the third requirement, we make a key observation on our own, and to demonstrate that, I show a histogram here, where these are samples that are evaluated with an analytical model to measure their energy delay product, which is a performance metric. And we take those same samples and measure their energy delay product using RTL simulation. And we see that the distributions are fairly similar. And of course, this isn't very surprising because the whole purpose of an analytical model is to accurately predict performance of hardware. But we do recognize that there is something that can be exploited here. And specifically, we can apply a technique called transfer learning, by which knowledge from predicting one task is reused for predicting another task. And so our second key contribution is that we use transfer learning to warm up the surrogate model with easy to collect data from an analytical model so that we can reduce the required amount of hard to collect data using RTL simulation. And sort of as an additional contribution, we also synthesize the methodologies from prior work, which hadn't been done before. And so with this contribution, we now satisfy the third requirement. So given our insights, we build the surrogate model Starlight as follows. First, we train a neural network, which we call the source model, on a large data set of analytical model samples. Then we transfer the weights from the source model to a new model based on deep kernel learning, and that model is Starlight. And finally, we fine-tune Starlight on a small data set of RTL simulation samples. The source model architecture is as follows. The inputs to the model are the DLA architecture and software mappings, and they're fed into a type of neural network called a variational autoencoder. At a high level, a variational autoencoder learns to compress a high-dimension input space into a low-dimension representation. And this is useful because, as you may recall, Gaussian processes work when the work best when the dimensionality is low. And in this case, we're actually able to lower the dimensionality down to 2, with still achieving pretty high accuracy. And that representation is fed, for now, into a neural network that makes a performance prediction. And this whole model is trained on the large analytical model data set. And this is the source model. So to build Starlight, we transfer the weights of the variational autoencoder from the source model. So we get our 2D representation that is already warmed up. And then we replace the neural network predictor with a Gaussian process. And this is the methodology of deep kernel learning. And that outputs the prediction as a Gaussian distribution. And then we train this whole model on a small RTL simulation data set. So now I show the accuracy of using this approach. Here, the x-axis shows the true performance measured by RTL simulation. And the y-axis shows the predicted performance measured by Starlight. And so perfect accuracy would be the line y equals x. And I plot samples from a test set. And we can see by the closeness to the line y equals x that Starlight is achieving high accuracy. And then we also measure the Spearman rank correlation, which is represented as rho. And that's a way, as I mentioned earlier, to measure the relative order of samplings. And that's important for hardware software co-design because the absolute prediction isn't quite as important as making sure you're making good predictions in general or picking good designs in general. And so Starlight achieves a high row of 0.99. So we also conduct another experiment to validate our uses of transfer learning and deep kernel learning. What we do is we show the Spearman rank correlation for different models by after we vary the amount of training data that's used. And so first we show Starlight. This is training data of the RTL simulation data set. So this line represents the mean across 10 independent trials of training, and the shaded region is one standard deviation across those trials. And we can see that Starlight achieves high accuracy even with just 400 samples of RTL simulation data. And it improves with more data, of course. So
Accuracy or correlation?
the y-axis is accuracy, measured by Spearman rank correlation. Sorry. Yeah, rho. Spearman rank correlation. Sorry.
Standard deviation here done on?
So I trained Starlight for each of these points 10 independent times. And it's the standard deviation of the correlation, yeah, of the Spearman rank correlation. So that's how Starlight behaves. And I now show a model which is similar to the architecture of the source model. So it uses transfer learning, but it uses a neural network predictor instead of a Gaussian process. And this approach achieves high accuracy, but not quite as high as Starlight. And this approach couldn't be used as a surrogate model anyway, because the predictor network is a neural network. But it does show that deep kernel learning not only achieves higher accuracy across the board, but also that it enables the model to be used as a surrogate model. So we also validate our use of transfer learning. To do that, we compare against two different models. The first is just a direct fine-tuning of the source model. So we train the source model on first the analytical model data set, and then we just fine-tune it with the RTL simulation data set. And so it also achieves high accuracy, but not quite as much as Starlight. And we also try an approach where we take the architecture of Starlight, which is a deep kernel learning model, and train it completely from scratch with no transfer learning, and that achieves pretty poor accuracy. And so both of these comparisons validate our use of transfer learning to warm up the surrogate model. Okay, so with Starlight, I've shown how we can accurately predict the performance measured by RTL simulation. And the last piece of work that I present is Polaris, which is a hardware software co-design tool that builds on Starlight to reduce development effort later in the DLA cycle, specifically when RTL simulation is being used. So first is a quick recap of what a hardware software co-design tool looks like. The inputs are a hardware budget and deep learning models, and the outputs are an optimized DLA and optimized software mappings. For Spotlight, those designs in the optimization loop were evaluated using an analytical model. And in general, actually all published prior work in this area performs optimization on some kind of proxy model. The proxy model may be modeling RTL simulation, or it may be an analytical model. But there's a fundamental issue here, which is that the proxy model may be inaccurate because it could have blind spots that it's just not modeling real hardware accurately. So when these optimizers make these so-called optimized designs, they may not actually be optimized when they're measured using RTL simulation. And so this is one of our goals that we aim to change with Polaris, which actually performs RTL simulation for the first time in the optimization loop. And this way, Polaris can ensure that the designs that it's finding are optimized as implemented. So these are the requirements for Polaris. First of all, as I just mentioned, Polaris should evaluate designs in the optimization loop with RTL simulation. And because RTL simulation is so slow, Polaris should be extremely sample efficient, even more so than Spotlight was. So the main challenge with Polaris is not the hardest of topics, but it's really just infrastructure. Specifically, it's hard to find open source DLA implementations and tooling. And so it's not the most interesting problem, but we did spend several months evaluating different frameworks and tool chains. And even after we picked one, it still took us several months to actually get the tool chain to work. And so what we settled on was using the Gemini DLA out of their Chipyard framework from Berkeley. Gemini exposes a flexible design space that can be explored by Polaris, and it can also be evaluated with RTL simulation on AWS instances. So we don't need to have our own infrastructure to do that. And we use the FireSim RTL simulator, which accelerates RTL simulation using an FPGA. And so with this tooling, we satisfy nominally the first requirement. And for the second requirement, we lean back on Bayesian optimization, which is known to be sample efficient. And as you recall, or as you may recall, the Bayesian optimization has two components. The first is a surrogate model, and we built Starlight from the ground up to serve that purpose. And then we also have the acquisition function. And again, just like with Spotlight, we just empirically find this, and we also find the same acquisition function works quite well, upper confidence bound. And so we're now satisfied our second requirement. And in fact, Polaris is mostly just an infrastructure wrapper around Starlight. So we evaluate Polaris, and to do so, we compare the designs it produces against designs produced by 3 other hardware-software co-design baselines. First is something of our own creation called offline random. The way that works is offline random draws random samples from the design space. It's drawing hundreds of thousands of samples and evaluates them just on Starlight. It doesn't actually use RTL simulation. And it selects the design that Starlight predicts to be the best. And then we evaluate that final design using RTL simulation. And we also compare against DOSA, which is a state-of-the-art hardware-software co-design tool. And that also optimizes a proxy model separately and evaluates the final design using RTL simulation. So we call both of those the offline methods. And then we also compare against Spotlight, and we adapt the methodology of Spotlight so that it can be used in this infrastructure in an online method, where it's evaluating RTL simulation in the optimization loop. And we compare those baselines using 3 vision models of different shapes and sizes: ResNet 50, RetinaNet, and UNet, and 1 natural language processing model, which is BERT. So here on the y-axis, I plot the energy delay product, which is, again, it's a measure of performance.
How old are those models?
ResNet,
Models.
let's see, ResNet 50 is from 2016. RetinaNet, I think 2019. UNet is also around. Yeah, they're pretty old. The reason we chose these models is because these are the ones that DOSA evaluates against, and we wanted to directly compare against it. But there's no, I guess, fundamental restriction, like we had to only exploit these models. Okay, so yeah, we have our energy delay product, and lower is better here. And so this is the performance of the designs produced by the offline methods. And this is the performance of the designs produced by the online methods. Now we can see that the online methods produce designs with significantly lower energy delay product than those produced by offline methods. And what's interesting here is that Spotlight actually finds pretty good designs, and I will get back to that shortly. But first, we can just plot the results for the other 3 models as well. And we see across the board that the online methods always outperform the designs produced by offline methods. And of those, Polaris always picks the best designs. So these graphs don't show the complete comparison between Spotlight and Polaris. And to do that, we need to look a little bit at the runtime of how these optimizers are working. So we run Spotlight and Polaris. And for Spotlight, we find that it spends 0.3 hours in the optimizer. So this is where it's training the surrogate model and selecting which candidates to evaluate. And then if you include the entire run with all the RTL simulations, all of the training, it takes 12.5 hours. And the designs it produces don't beat DOSA until the 28th iteration of running the optimizer. On the other hand, with Polaris, the time spent in the optimizer is significantly higher. It's 5.3 hours. And that's because we're using the deep kernel learning approach, which is slower to train And also because we have to train that model with the RTL simulation data set and all the evaluated samples. So it's being trained on much more data. And so it's significantly slower. But what we find is that the overall runtime of running Polaris, which includes the optimization time and RTL simulation, is actually shorter than Spotlight. And that's because the runtime of RTL simulation is directly correlated with the cycle count of the designs being evaluated. And Polaris is picking designs with significantly shorter cycle counts. And so it's picking much better designs than Spotlight on average. And that's why the overall optimization, overall runtime is much lower. And that's also corroborated by the fact that it only takes Polaris 3 samples, 3 iterations before it can beat the designs produced by DOSA. And so, of course, that's not free because we do have to collect that RTL simulation data set. And it is 820 samples. It took about a day to collect. But in practice, tools like Spotlight and Polaris are run every time some design parameter changes so that you could explore the optimal parameters values for other parameters. And so that cost kind of gets amortized across all the runs of Polaris. Okay, so now I've shown how our work can save development effort in the earlier and later stages of DLA development, and I go ahead and finish up with the conclusion. Design space exploration is challenging because there's many tunable parameters, and those parameters have complex interactions among each other. To overcome this challenge, I show how we can leverage prior knowledge. Specifically, I showed how to inject handcrafted domain information to guide design space exploration and how to efficiently train a surrogate model using transfer learning. And the deliverables of this work are 3 open source tools that reduce the cost of DLA development, and also methodologies that may be more broadly applicable than what I've shown here. So to conclude, deep learning consumes significant resources. And DLAs are an important tool for us to mitigate the cost of deep learning. But DLAs are costly and time-consuming to develop, and because so many people are developing them, DLA development costs are multiplied widely across the industry. So our work reduces the cost of DLA development, thus enabling more DLAs to be developed to mitigate the cost of deep learning in the future. So now I'd just like to thank a few people. First of all, I want to thank Calvin, who's patiently guided me through this journey. In addition to teaching me how to conduct good research and articulate my thoughts clearly, he also encouraged me to lead a well-balanced lifestyle. And then I also want to thank the rest of my committee who have given me excellent feedback to improve the quality of my research. And with specific thanks to Derek and Matan for all the different interactions and work that we've done together at my time at UT. And I also thank all the students that I've worked closely with because they've given me lots of thoughtful feedback and have been great to brainstorm ideas with. And I could keep going, but thank you to friends, acquaintances, students I've mentored, everyone who attended this talk, and of course, my family. So with that, I'll open the floor to questions. Yeah.
Maybe really dumb question. Does the DR compute just the maps or like are we doing activation functions and stuff?
For Polaris, it does everything. For Spotlight, since it's using an analytical model, it's just like the bulk of the computation, you could say, which is the convolution. And then for Polaris, it's actually implemented in C using like Gemini's ISA. So it's doing the whole model. Yeah.
You have something like how sparse the design space is. I guess like you painted this picture of like all these drop-offs and everything's disconnected. But like, I mean, how bad this is going to get?
I don't have like a way to quantify that. What I found is that if you just do like, say, unconstrained random search, you just draw random samples from the design space, about like 70% of them end up just failing. So it's pretty sparse. And so kind of for feasibility in both of these tools, we do implement some reasonable constraints on the design space that should still be, you should still be able to find good designs. But I don't have any other quantification of that. So that's it. I'll go first.
Can you repeat the questions, by the way?
Oh, yes, sorry.
Yeah, thanks.
Okay.
So, in practice, have you found any parameters to be were more consistently important to optimizing the model, such as like, I don't know, if you get like the top 10 designs out, and like across them, the tiling doesn't change that much, but underlying.
Yeah, I actually have a slide for that.
Maybe you can repeat the question.
Yes, so the question, sorry, I'm so bad at that, sorry. The question was, have we found any design parameters that are especially important? And we did actually measure this. So this was it's not exactly what you asked, but this was for Spotlight. We measured the importance of the different features that we build. And we find not really actually. It does depend on the model that's being optimized, which parameters are most important. So what I'm showing here is, if you look at, say, like VGG 16, this is just like a measurement of importance for each input parameter. It's called permutation importance. Basically, you wiggle the inputs and see how big of a change it makes in the output prediction. And so I mean, some of them, for instance, with transformer, the parallelism available in the kernel, that's kind of like a proxy for utilization, sort of, has a pretty significant impact.
Yeah, this is your feature.
Yeah, so
it doesn't mean what the
I know.
value
Yeah, so that's why I said it didn't directly answer the question. I can run this experiment and see, but I guess just like running the stuff and kind of intuitively seeing how it works, the answer is kind of similar. It varies a lot between models, like what actually gets focused on. And also, it varies with like the evaluation framework being used. So for instance, with Spotlight, we find that depending on which analytical model we use, because we can actually support two, it may decide to favor really narrow and long systolic arrays. And I think that's likely an artifact of the analytical model rather than that actually being a good design. Okay, and then you had a question. Okay. Yeah, I mean, I can perform this experiment on the input feature space as well. I think that would be interesting. I did at some point. I don't remember the results. Yeah.
What do you do with the, how are you modeling data when it moves between layers? Does it go back to DRAM or?
Yeah, so both of these implementations, they're not actually using, well, analytical model for sure, but even Polaris, it's not using, so to speak, industry grade version. So it actually just does it layer by layer still. And it doesn't try to like do pipelining or anything like that. So there are limitations, and that's just infrastructure challenges. Oh, and sorry, the question, keep forgetting, was, are we doing this layer by layer, or are we modeling the behavior like across layers, the data movement across layers? Yes.
Yeah, great talk, Shrod. So I noticed that you tend to use domain-specific features to reduce the dimensionality. Have you considered like some other like more like, I guess, rigorous method like PCA to reduce dimensionality? And if so, like, did that perform better or worse? Or like, what was kind of like the decision to do these domain-specific features? Like, how did that kind of come about?
Yeah, so the question was, have we tried using more rigorous methods like PCA to reduce the dimension of the input space? And not exactly. When we were building Spotlight, then we were really trying to emphasize sample efficiency. And so we played some tricks, like the Gaussian process that we use as a surrogate model is not what you would typically use, but it trains a lot faster. And so just reducing the dimensionality of the input space wouldn't have been sufficient for that kind of surrogate model to be accurate. And it wasn't accurate anyway, I guess, in the end. But that's why we wanted to introduce this like feature, this handcrafted feature transformation, so it can be essentially fine-tuned for exactly the kind of surrogate model we were using. And I do have some results. I don't know if I have them in my slides, but Spotlight does achieve the sample efficiency. It does it does plateau when finding designs like fairly quickly compared to other things like random search. Yeah.
Interesting insights you found from like looking at the final like model that Polaris released, seeing if they matched up with what you expected it would make from the way to write software.
The question was, have we looked at the results of the designs produced by Polaris and Spotlight and found anything interesting? Not something that's immediately interesting as just like someone looking at the designs. It's not doing anything crazy, except for that case I mentioned earlier where Spotlight, for some cases, was producing this narrow systolic array. We did find for the infrastructure you're using for Polaris, the size of the compute cluster or like this systolic array has a pretty significant impact on the energy delay product. And generally speaking, with that infrastructure, larger systolic arrays perform better. And that kind of makes sense for things like UNet was one of the models we evaluate, which is like a really big network. And so it can actually fully utilize like a big systolic array. But I wouldn't say we found anything. I don't think we like derived any interesting insights about hardware design from either. Okay, yeah.
How hard would it be to add throughput as a parameter? So you talk a lot about latency, but when you look at like actual servers, you want to look at throughput as a very like decisive thing for power.
Yeah.
Because you're gonna have a lot of inputs and like data management's really important. So like, is that possible?
Yeah. So the question was, how do we incorporate throughput? I'm not sure if this is the exact answer, but we do actually, Spotlight can optimize different metrics. We optimize delay. We also optimize energy delay product, and we can also optimize throughput. So we would be maximizing throughput. And because you can give it area and power constraints, then you can say like, this is my power budget. What is the maximum throughput I can achieve? And there's nothing fundamental to our tools that would restrict us from doing that. It's more of like, can we get those measurements out of our simulators and models?
I think I just missed this from earlier in your talk as I was driving, but you showed a 7-layer convolution or 7-nested loop convolution and like other I guess this question is mostly like on the software design, software exploration of your design space. How tied are you to like a given implementation of the algorithm? As in like, are we only exploring certain implementations of convolutions, let's say, because like, if I wanted to do another type of convolution because it's more algorithmically efficient, let's say I do FFT transformation or something like that, like would the tool just be able to pick up any like broad structure of my algorithm, or are we targeting specific like ways to implement a certain convolution?
So for this work, we do the standard convolution, which is, it has those 7 parameters. It also has stride and dilation, which I didn't mention. And that can model things like pointwise and depthwise convolution. But it can't do something like an FFT transformation. And I can't make claims about like whether our tooling could learn the behavior of that, but there's no fundamental limitation of trying different inputs. It's just how you represent that set of transformations. And so if you can represent the set of transformations for FFT using some parameters, then you can presumably, and I haven't tried this, so I don't actually know, just optimize those parameters.
But I'm not like arbitrarily co-designing against like high level code. I'm like, I need some sort of structured representation of what the algorithm.
Yeah. I mean, that's just because you need to be able to define a design space. And that kind of, that you would have to have some clear algorithm for that. And Calvin, you had a question?
Okay, so first I have a comment. So runtime doesn't mean what you think it means. Runtime is the phase that's storing execution rather than compile time. So you meant
Okay.
running time.
Yeah. Wall
time.
clock time or
Yeah.
something. Sorry. The question there was runtime was not the right term to use. That wasn't a question,
So my question
a comment.
is that there have been a couple questions from the audience about, well, after the fact, can you do some analysis and
Hey, Chirag, I can't hear you.
Oh, hello. Can you hear me on Zoom? No?
I can hear you.
Oh, okay. Thank you.
So my question is, there've been a couple of questions from the audience about, are some features more important, or afterwards, when you analyze the resulting designs, you get some conclusions about what make good designs. And your answer sort of says, well, no, we don't. So is this a strength of your work or weakness of your work? Is this motivate your work or, yeah, whatever.
Okay. Yeah, so okay, the question was that a few audience members have asked if we can get any like intuition from the designs produced by these tools. And my answer has been like, no, not really. So the question was, is that a strength or a weakness? And I would say it's actually maybe not a strength, but it is indicative that this sort of design, first of all, it can be automated. DSE can be automated because it is able to find designs. We showed that it can beat the hand-designed accelerators. And also, in reality, like it is hard to do like parameter sweeps and all this, and it takes a lot of effort. So at the very least, you can reduce the effort. In that sense, I think it's a win because we can get good optimized designs. And it may be indicative that like we're at this crossing point where like if we need to do design space exploration, like on this huge design space for like a whole system, maybe it like really is hard for humans to do that manually. So automation could be good in that regard. But I mean, at the very least, it does save the effort of having to do it.
You're saying the value of intuition is going down.
No, I'm not saying that. The comment was, is the value of intuition going down? No, because with Spotlight, like we still need that domain expertise to actually converge. And I have results that show the domain information is significant in making the tool converge. But what I'm saying is that it's more like, this is another tool that architects have to evaluate designs and to make things. And I don't think that's a bad thing.
Well, maybe
But
you can rephrase Curtis's question as the limits of intuition are approaching or something.
Yeah, I don't know if the limits of intuition are approaching, but right now I think both approaches, intuition and these tools, at least in their current form, go hand in hand. I don't think one is like replacing the other.
Can you show slide 67? So you had on the y-axis row, okay, yeah. So we were looking at this, and we're like, wow, Starlight's definitely winning here. But I'm looking at this and I'm thinking, okay, well, suppose we didn't have the green your solution, and we were stuck with one of the others. I still have a pretty high row value.
Yeah.
So following through and imagine you didn't have that, where would I end up, like on slide 82 or something? And around 80 to 82, you've got like how tricky to do some stuff, and then how good your designs were, where you had 4 bars. What would that end up looking like?
Yeah.
Maybe repeat the question.
Yeah. So the question was, those other models that we evaluated also achieve pretty high accuracy. A couple of them just can't be used because they're like neural networks, but the deep kernel learning approach would have achieved higher accuracy. And so the question here is like, how important is the accuracy in the ultimate results that get produced? And I haven't evaluated that. But judging by the fact that Spotlight does well in its own evaluation and in this evaluation, I don't actually think the accuracy is very significant. It's one of those things where if you can get higher accuracy, you should. And it does enable things like, for instance, this offline random approach would likely perform pretty badly, even if the accuracy drops a little bit. I mean, and it's not doing terribly here except for in BERT, because it is still outperforming DOSA in 2 of the cases. So accuracy is one of those things where it's beneficial to have. I don't know I can't quantify the exact benefit.
Yeah.
Okay. All right.
So I know you're headed off to industry, but if you were gonna stick around or continue this work somewhere else, what do you continue? Is your analytical model the weakest point in this? That seems likely from that 11% number at the beginning, and possibly you could find better optima with the RTL refinement with a better analytical model. But do you have a sense for like what the weak link that improvement is?
Yeah, so the question is essentially what would I do next? What would I change given like all the results we've made of Spotlight or Polaris or do next? So Spotlight, so okay. Even doing like random search, you can eventually get like good results. And so really what we've sought in both of these pieces of work is sample efficiency. And there's sort of two different ways to do it. One of them is handcrafted features, and one of them is learned features, essentially, using a variational autoencoder. Something that, well, Matan kind of hinted at earlier was which approach is better. And that's not something I've directly compared. I think there's pros and cons to both, but I think a quantitative analysis of which approach is better, or if there's a way to combine the two approaches, which intuitively there are ways to combine the approaches. I think that'd be like the next thing I would be interested in, because what I'm imagining is if handcrafted domain information improves sample efficiency, and if transfer learning and using some learned model improves sample efficiency, maybe you can do even better if you combine the approaches. And the tools are meant for different purposes. Like if you're evaluating designs on an analytical model, you're not going to wait 5.3 hours to optimize that because the optimizer is so slow for Polaris. So I guess like all things, there's kind of trade-offs between them. And I'm kind of interested in like evaluating more rigorously which of those approaches is better, worse, in which scenario, in different scenarios.